Let's get started. Today I'm going to continue with the lecture on probability. We'll actually finish up today and start with queuing theory on Tuesday. Okay, so the topics today are sort of a grab bag of things. I'll finish with the last of the continuous distributions, the power law distribution, and then state some theorems. They're not going to prove it, of course. But these are kind of a useful collection of theorems, something you should know. And we'll end up using some of these as we study statistics, so it's just useful to state them right here. And then the bulk of the lecture, maybe, well, about half, a little bit more than half, will be on really what is meant by joint probability distribution. And this concept of joint probability is something that many students find confusing. And so I'll try to explain it through a very, very simple example, and we'll sort of slowly make it more and more complicated. And at the end, hopefully, you have a good understanding of what a joint probability distribution means, and what a marginal means, and conditional joint probability, and so on. And that will allow us to motivate a technique for computing joint probability distributions, or I should say metrics related to joint probability distributions using Bayesian networks. So we can view Bayesian networks as a compact representation of joint probability distributions. So we'll spend quite a bit of Bayesian networks. And Bayesian networks shows up a lot when you're doing any kind of reasoning, AI systems, machine learning. They all use Bayesian networks, and you may run across them elsewhere. But I think it's viewed properly as being a subset of the joint probability distribution, which I have misspelled. Okay, so let's start at the top with the power law. So we saw in the last lecture, some laws that show up when, for example, the Gaussian shows up or the normal shows up, and you have some expectation and you have some variation, a little bit of variation around it, and you model that as a Gaussian, as a normal distribution. Another kind of pattern that shows up quite often is that we have some ensemble or some set of objects. Let's just call them, object. Let's call it A1, A2, etc. Let's say we have AN, and N is large. Okay, and moreover, what we find is that some objects are more preferred than others. Some objects get in terms of accesses, are accessed more than others, are referred to more than others, whatever, right? And so we have an ordering, and we assume, for example, that you impose the ordering over here, and we'll say that A1 in some sense is A2, and this notation here just means it's preferred to, etc. Okay, and what we can then do is we can think of, for example, the histogram of the number of accesses. So let me make it a bit more concrete. Let's say that you have a library with 1,000 books or 1,000,000 books in it. Okay, the Davis Center library. Now, you can imagine that some books have not been checked out since 1954 or 1957, whenever they set it up. Nobody ever checked it out. Why? Because it's a book that nobody really wants to read. It's a read once, or say write once book. It's written once and nobody read it, so nobody checked it out. So it has essentially 0 accesses, and so it will show up as AN. Basic number of accesses for this is 0. And in fact, one could expect that the number of items with very few accesses, 0, 1, or 2 in the last 50 years, is actually quite large. One can actually expect that maybe 99% of the books in the library, if you have 1,000,000 books, chances are pretty good that of the 1,000,000, only about 10,000 have been checked out more than twice in 50 years. Okay, that's probably true. All right, the textbooks have been checked out, and maybe a few others, and the rest have never been checked out. So what we expect to find is that if you were to draw the histogram, we would have at 0 a lot of books would have 0. Here I'm ranking. Over here is the index, and on the y-axis I have the number of accesses to that. Okay. And so there's lots of 0, and then turning your attention to the other side, some books are going to be checked out a lot. Let's say a course textbook for algorithms. Every term, everybody's going to rush and get that. So there's going to be a lot of accesses to some things over here. This one, probably the next most accessed one, is also pretty up. But you know what? It drops off pretty fast. And we get a few in the middle, and then we get nothing else. Okay. So we have this behavior where the accesses to certain things are way more. In fact, if you were to look at the total number of books checked out, almost all the total number of books checked out would actually belong to the first few of these. Okay, so similar situation holds. For example, if you're at Amazon and you're looking at books sold, okay, the books that are ranked the most popular ones, the 100,000 most popular books, probably account for most of the accesses. And then there is this tail of books that are sold ones and twos and so on and so forth. Okay. Another similar situation shows up in if you look at the inter-arrival times of packets to a router. When they say inter-arrival times follow power law distribution, that means that you have lots of packets that are close together. So if you were to look at the inter-arrival times that were to, let's say the inter-arrival time, this is 1 second, and then we have inter-arrival time of 2 seconds, and so on, using some quantum. One could postulate that if you have a burst and you're getting packets essentially back to back with 0 gaps between them, that becomes very popular, right? Because you have bursts of packets coming back to back, whereas other times are going to be less popular. So this inter-arrival time thing I'm sort of making up, but these other things are certainly observed. So in these kinds of situations, we see what's called the power law. Okay. Now, I should mention that there are actually two related rules. One is called Zipf's law, or the Zipf distribution. Okay, and that's discrete. And that's exactly what I've been showing over here, is a discrete distribution where the domain, okay, is essentially the set over here, where it's the objects in the ensemble, and we're looking at the number of accesses to it. And we can view the axis divided by essentially AI divided by sigma AI as being essentially the probability. Okay, we define the probability of the ith book being checked out as being sigma AI or sigma AI. That is your frequentist approach to probability, and we can view that as being a discrete probability distribution over the entities A1 to AN. And so we can say over here that we have discrete probability distribution, and roughly speaking, basically P, the probability that the random variable takes the value AI is essentially something that looks like this, is a to the minus I, where you have some parameters. So we have I'm sorry, what am I doing here? I to the minus a, I to the minus alpha, we just use alpha as a thing. Okay, so essentially what you're saying that the ith value over here, which is something over here, goes down roughly like this. Okay, so to take an example, if the you have I is 20, then the probability of the 20th thing we access is 1 over 400 if alpha is 2. So if I is 20, alpha is 2, then the 20th item is going to be accessed 1 over 400 times, the 30th item 1 over 900 times, and so on. So it decays fairly fast. So this is Zipf's law, and the continuous approximation to this is called the power law. Okay, so when we take the number of items going to infinity, then we can write down the general form of this is that fx, so the power law, fx equals, there's a parameter alpha minus 1 over x min, which is the smallest value that you can take in the domain, x over x min to the power minus alpha. So the x min parameter essentially allows you to do a certain amount of normalization if you need to, which says that's the smallest value x can take, and we have to make sure that alpha is greater than 1, because obviously you can't have a negative there, so alpha is greater than 1. And this is the density function. Now I'm leaving out a normalization term. In fact, we see that if alpha is less than 2, okay, then the expectation of x, which is defined in this fashion, is actually infinite. All right. So what this means is that you're going to have it's basically undefined, and you're going to have this increasingly large values. So for all practical purposes, though alpha less than 2 is okay in this formula, in practice, if alpha has to be greater than 2, okay, we want it to decay fairly fast. Otherwise, there's too much mass in this thing. I'm going to say one more thing, and maybe that will help you understand this. Essentially, what we can do is something like this. We can think of log of f of x, okay, is nothing more than, it's basically given approximately alpha log of x. Okay, so what does this mean? Okay, if I view this as, in the continuous sense, as p of x or f of x, then on a log-log scale, so if I have on this scale log x and I have here log f of x, I expect to see essentially a straight line. And what is the curve? The curve is, the slope is minus alpha. Okay? So I should probably put over here minus alpha log of x. Okay? So what we're saying over here is something fairly strong. What this says is that let's take the ensemble, let's look at the number of axes, and we will plot it in a sorted fashion, okay, which means the most axis one is called number 1 and number 2, and let's take the limit as n tends to infinity, and what we're going to get over here is if we plot log x versus log f of x, this is a straight line. In a discrete case, of course, what we expect to see are points that look like this, okay, and in fact, that's exactly what we get. If we were to take the number of accesses to the most checked out book and call that 1, the second checked out book, call it 2, etc., and you have to plug the log of the book ID versus the number, the frequentist approach, the ratio of the number of accesses to total number of accesses. In other words, this value over here, where did I put it? This value over here. Then it turns out that in fact it is a straight line exactly like this. Okay, and the slope tells you what the value of alpha is. So that is a empirical observation which we're trying to capture using the power law. Okay, so in the same way the normal is trying to capture the variations in expected mean, here we're saying that it's not like a book is normally checked out 3 times, over 3 times a year, and some are at 2.9, some are at 2.6, etc., and there's a little bit of variation around 3. No, it's not like that at all. It's the opposite. Some books are checked out 3, some books are checked out 3,000, okay, and some books are checked out 0, and that's what's going on over here. Okay, so that's why you're getting this shape as opposed to a normal where you have a little bit of variation. There's a tremendous amount of variation over here, and in fact, as you can, if you compute the variance of this is alpha between 1 and 2, it's infinite as well, as far as I remember. Yes?
I think the example which we took over here, they might seem reasonable even if we take the exponential decay distribution.
Okay, yes, I'm coming to that. Yes, exponential versus power law, I'll come to in just a minute. I just want to get the concept of this first. Okay, any questions about this over here so far? Okay, so I'll quickly summarize. What I'm saying over here is that we have a set, or in the continuous case, we have a range. Now, it gets a bit tricky when you say, well, how do you do the ordering on the range? Because the range is a continuous range. So we have to assume that, the range is such that there is a natural inherent ordering. For example, interarrival times, there may be a natural inherent ordering in that continuous range. Obviously, for number of books, is a discrete range. And then we have distribution, where we take this definition of probability, and we can define that the probability that it takes the ith value is essentially the ith value raised to some constant negative power called alpha. And in the continuous case, other than the x-min, it's basically similar, and I left out the normalizing factor, and the characteristic signature is this. Okay, so this is what I've said so far. Now, the question that Aniket asks is this: we've already seen a function which looks like this, which is the sort of the exponential. In the exponential case, it kind of looks like this, right? And what's going on over here? Basically, if y equals e to the minus x, then log y. Okay, I should probably show fx just to be. Fx is e to the minus x, then log of f of x is equal to, well, it's just minus x, right? So what happens over here is that here we have a ratio of log of x versus minus x, and maybe an easier way to describe it is that in the power law has way more mass towards the right hand side than exponential for the same value. Okay, so I'm sorry.
They call it fat tail.
The fat tail, heavy tail. So I'm going to come to that in just a second. If you were to zoom in to the distribution, what will happen is that, on a linear scale, they both sort of look like this. Okay, you kind of go down like that, and if you plot power law and exponential, they both look like that. But what happens is that if you plot those out, you'll find that essentially the power law looks like this, okay, and the exponential is going to look like minus, on a log scale, it look like minus x, and how am I going to draw this? So this is going to be minus alpha versus minus x. Okay, so the slope of this is minus alpha log x. So the thing is, drawing x on a log scale is a bit crazy, right? It's going to be essentially going exponentially down, okay, because this value here is, this is on the x-axis is log of x, and this is over here is sort of x. If I'm getting this correct, or minus x, I guess you have to take the appropriate thing down. I have tried figuring this out, and I can't really understand how to draw this properly, but I'll tell you what. If you look at the homework question, I don't know which one it is, I have a table there where I ask you to draw. I ask you to compare the value of the power law versus exponential for certain values of x. Okay, and you'll find that the order of magnitude gap between what the power law says and what exponential says is, like 10 to the 44 orders of magnitude difference for n equals 50, for example. So if alpha is 2, the exponential is way, way, way smaller than the power law, and that's why we call it fat tail or heavy tail. So even though the power law is going down fast, the exponential is going down much faster. Okay, so for n equals 50, for example, the exponential has like 10 to the minus 50 roughly, or something like that. I don't remember the exact numbers, but power law still has something that is non-zero, and this is actually why they call it the long tail or the fat tail. And there is this book that came out about a couple of years back saying that because it's a power law and not exponential, what's going on is that there is some non-zero mass towards the tail. And so if somebody is going to have something that caters to quote-unquote the long tail, from a business perspective, they can make a lot of money. So and the story here is something like this. Let's say that the distribution of books was in fact exponential and not power law. The distribution of sales of books was exponential and not power law. That means that this bookstore, which is the size of this room, would actually carry like 99.999% of all the books that everybody would ever want. Okay, there's no point in having a larger bookstore because the amount of money you can make on selling this is not enough. However, if the distribution is power law, what that means is that there's enough mass in the tail that I need a very large bookstore. And I can't build a very large bookstore because, it takes much space for that. I have to have it heated, and I've got to have whatever. It's expensive. It's real estate. However, what Amazon does is to say, look, the bookstore is in the sky. You have this virtual bookstore, and all the books are actually sitting, in some warehouse. In fact, Amazon will actually print a book for you if you want to, right? If you say, I want to buy so-and-so book, it's not there. They tell the publisher, hey, just print it. And you have these mini printers now. You can actually print these on demand. So the bookstore essentially is infinite, which means you can capture all the mass in the long tail. I mean, if you can capture all the mass in the long tail, no small bookstore can compete with you. So the argument is that very, very large internet-enabled e-commerce things like iTunes and Amazon are able to capture on the non-zero probability mass, or I should say non-insignificant probability mass in the tail of the distribution. That's what they call the long tail. So this is another reason of what's going on over here. Okay, applied to the packet arrival process. Okay, the packet inter-arrival times in packets are supposed to be, if the packet arrivals are described by Poisson, as I mentioned, and we'll study more in queuing theory, the inter-arrival process is exponential. Again, we'll see that later in about a week from today, or maybe 2 weeks from today. And the inter-arrival processes are actually shown to be power law. So what that means is that with exponential, the probability of a very long inter-arrival time is practically zero. Okay, it's going to be very, very, very small. With power law, there's a non-zero probability that actually you're going to see larger inter-arrival times. Okay, so it works both ways. Okay, so I think that's who was asking what. So that's a power law versus exponential. Now in the notes, all I have is one line saying that power law is greater than exponential, but and I think the numerical will really help you understand how much of a gap there is. But there's a considerable body of business literature on this, which which of course I'm not going to go into over here. Okay. Any other questions about this over here? So the other example I have in the book is for website visits, and I guess you can take a look. This is I copied these two figures from a paper called Zip Power Laws in Pareto, and what they're showing over here is, if you have it in front of you, is on the x-axis on the left-hand side is this graph over here, which is it looks kind of drops off very fast, and if you look at the log scale. However, it's a discrete thing because you look at number of visitors to websites. So you say, okay, how many visitors go to google.com, how many visitors go to whatever, chapters.ca, and you have that number of accesses to a website. And sure enough, empirically, you see that it looks pretty much like a straight line, and that is your power law in the discrete case. Okay. Any questions about this? Okay. All right. I'm going to so change gears now. So that was the last of the continuous. I kind of snuck in the discrete as well over here, and we'll start talking about these different bounds and theorems that are useful to have. So these theorems or bounds are useful when you have some kind of you want to get some sense of what is the tail probability. So let me start with the first one. This is called the Markov Inequality. And the Markov Inequality, okay, what you're given is a random variable. Let's just call a random variable, which we call x, and we are told that the expected value of x is mu, and that's all you know about it. The expected value of x is mu. That's it. It could be any distribution whatsoever. Any distribution whatsoever. We don't know what the distribution is. All we know is that the probability mass under the distribution curve is 1, and that's basically all you know about it. So what you want to do is we can think of the distribution like this. So here we have the value x, and you have the value fx, and it could be anything. Okay, it could be over an infinite domain, or it could be a non-infinite domain. It could go all over the place, right? As long as the area is under 1. Area under the curve is 1. So we want to say that here is some value a, some constant a, and I want to know what is the probability that x is greater than or equal to a. Okay, and so it's at first glance it looks crazy. How can I know? I mean, the distribution could be whatsoever, anything whatsoever. But it turns out that if we know that the mean is mu, that kind of constrains us. Okay, intuitively what's going on is that the mean, which is say some value over here, okay, if there's a lot of mass on the right hand side, then the mu is going to move to the right hand side as well. Okay, by having the mean be at some particular point for some value of x, you can't really have too much more very far away from the mean. In fact, we can show that probability that x is greater than or equal to a, this is the right hand side, is less than or equal to just mu over a. Okay, and so what we're saying is that as we move to the right hand side, the probability that x is larger than that value keeps decreasing. In fact, it decreases essentially linearly with a. Okay, so as you make something further and further away, this is what you're going to get. Okay, and I guess you have to have, I wonder if you have to have a greater than mu. I don't know. I should look that up. In my notes, I always assumed that a was greater than mu, but I have to check. Okay, I'll just check that. But that gives you kind of a rough and ready bound. Again, in the homework assignment, what you'll find is I've asked you to compute the Markov bound on some value compared to the, I guess it's either the Gaussian or the binomial, I can't remember which one. And you'll see that this bound is very, very, very loose. It can be like 10, 20 orders of magnitude loose. But it's better than nothing. Okay, so if you want just like a rough and ready bound, that's what you have. And of course, if you know something better, then you can plug it in. But it's really remarkably simple, and so it's a useful tool to have. Yes. If a is smaller than mu, yeah, but
and I think it's random variable must be positive.
So random variable has to be positive. Yeah, it has to be positive, yes, absolutely. So it is 0 bounded. So I should probably state that. Random variable x is greater than, I guess, I don't know if it's equal to or greater than, but yeah, and a is greater than 0 as well. I should probably state that as well. Otherwise, that doesn't work. So, but I don't know about, so if a is smaller than mu, yeah, it's not very helpful to you to say that it's less than 1. Yeah, so it's a trivial bound when it's less than when a is less than mu. Okay, anything else? Okay, so we'll go to something that's slightly more useful, or well, this is useful too, but this is called Chebyshevs Inequality. Now, it turns out that you can spell Chebyshev in about 100 different ways, with random assortments of C's and H's and T's. And I can't remember. Okay, I have CHEV here, and I think I put C. I don't know. I may have used S somewhere else. There was a joke I heard that in the Yale Computer Science Department, this is probably in the mid-'80s, the root password was Chebyshev, and you could tell somebody it's Chebyshev and they wouldn't know what the password was. Okay, because there's so many variations of the word Chebyshev. I picked one out of a hat, and I think I used 2 different ones because I have it one way in page 22 and different way on page 23. Anyway, so here we have, and let me be careful, so x is a random variable. Again, we don't know much about it. We do know it has a finite mean. I should probably say over there it's a finite mean as well. It's a finite mean mu, and it has a variance sigma squared. And for any constant a, now we don't have to say that a is positive. For any a, we can say the probability that x minus mu is greater than or equal to a is less than or equal to sigma square by a square. And so let's just sort of unpack this. So what's x minus mu mod? Well, again, we have over here some distribution. Again, it can be positive or negative in this case. And we're saying that it has some mean. Let's say this is the mean mu. And what we're doing is that we have some value a. And so this is a over here, and this is a over there as well. So we're saying that the distance of x from mu is greater than a. So it means this area here, the 2 tails, the left tail and the right tail, the sum of the masses in these 2 tails is bounded by this value sigma square by a square. Okay, and that's basically what we are saying. Now, what happens if a is negative? I guess it doesn't really make any sense. It doesn't really help you for a if a is negative or not. So again, typically a is positive, but again, I should probably check, is a positive? I think. Okay, I'll just double check on that. But my notes say it's for any a. So typically, again, I use it for positive a. What we're saying over here is that I don't know anything about the distribution function. However, I know the mean, and I know its variance, and now I can tell you the total mass on both sides. And if you know it's symmetric, then of course we can get a little bit better. We can get a handle on the left or the right. But if you don't know it's symmetric, that's all you get from the Chebyshevs inequality. Okay, and that is basically it. Again, this is useful when we have arbitrary distributions, and we want to get some idea of how bad can it be, you know. Because these kind of tail probabilities, these areas under the curve, in some sense are usually at the badness in the system. Okay, it's some measure of badness in a system. What do we mean by that? Let's say I'm designing a web server, all right, and I want to know what is the probability that the number of hits in any 5-minute period exceeds the capacity of the web server, because then I'll get the server is out of bound kind of thing, or server has too much, is busy. I don't want to give that busy signal. So that if I have some random distribution over the number of hits, okay, and I size it for that particular value, I size it over here, this tail probability is the bound on the amount of badness. So I can say, all right, I've bounded even using, even though I don't know the complete shape of the distribution, I kind of can tell you that this bound, even though I cannot do the mathematical integral on this or even the numerical integral on this, I can approximate it, and I can tell you that with 99.99% confidence, okay, because that's what this bound gives you, the number of visits to my website will not exceed certain value, okay, and so so the badness, which is getting the signal server is overloaded, is bounded. Okay. Similarly, we can bound packet loss probabilities in a buffer. So I have packets coming into a router, I have packets being served, and I want to size the buffer so that packets don't get lost. Well, again, the number of intensity of packets coming in is a random variable. It has some distribution. What I can do is I can say, okay, if the buffer is this big, the probability that it doesn't exceed it, I can bound using a Chebyshev or Markov bound. And that allows me to say, okay, packet loss probability is bounded. All right, so let me stop here for a second. We'll take a break, and we'll come back and talk about these other two things over here. So law of large numbers has two variants, weak law and strong law, and I'm going to tell you about the strong law of large numbers. And, people claim, at least people in probability theory claim this is one of the most important theorems in probability. I guess so. I mean, it's not something that that I've run into very often, but it's at the basis of many important theorems and proofs. So what does it say? Let me be very precise. So what we're saying over here is that we have some kind of random variable. And I should say, okay, right. So I have a set of random variables. And I'll call them, x1, x2, etc., until xn. Okay. Now what I'm going to do is that they are independent. I'm going to assume they're independent. And assume that they have the same distribution. Okay, so whatever the distribution is, I don't know what it is, but they're the same distribution, and these two are often standardized to IID, where independent identically distributed. So we'll say x1 to xn is a collection of IID random variables. It means you're independent and identically distributed random variables. And we also say that they have the same expected value which is equal to mu. Okay. Now, let me first state the theorem, and then I'll tell you how to understand, at least one way of understanding it. Limit n tends to infinity x1 plus x2 plus xn in plus mu equals 1. All right. So the way to understand it, okay, a way to understand it is this. I have some phenomenon going on, and what's going on is that I'm going to sample it. I'm going to measure its value, and each time I measure it, I call it x1, I call it x2, x3, right? So I assume that that phenomenon is such that each of these samples I'm getting are independent. Okay, and since it's the same phenomenon and the phenomenon hasn't changed, it's stable or stationary, they're all identically distributed. And in fact, the phenomenon has inherent or intrinsic mean value mu. What this says is that if I take the observations and sum it up and divide by n, the number of observations, I'll in fact find mu as n tends to infinity. I'm guaranteed that the mean of these samples in fact becomes the true mean. Okay, this is the mean of the samples is equal to the true mean with probability 1. Okay, so as long as we are making independent samples, all right, they will approach the true mean with probability 1. So let's take a kind of an example which is relevant. So there are two elections going on. So let's take the Canadian election, and we want to find out the probability that let's say Dion gets 30% of the votes. Okay, so we want to compute that probability, and so what is the, of course, no person is going to vote 30%, right? I mean, you can't say I'm going to vote 30% here, 30% there. So what we're going to do is that we're going to have some sample of, let's say, 100 people. I'm going to call them up, and I'm going to find out what fraction of them vote for Dion. Let's say, somebody in this particular first sample, 40% vote. In the second sample, 20% vote, etc., right? So we can view that if these samples are chosen in a way that is independent, right? So the first 100 people and the second 100 people are not talking to each other. They're not calling each other up on the phone and saying, hey, I said this, make sure you said the same thing as me, right? These are independently drawn. And how do we do that? You basically take a phone book and you spin a big wheel, and it lands on this number. You call them up and you say, hey, who are you going to vote for, right? And you do that, and that's what these sampling firms do. Then what we're saying over here is that if we can view each of these as a random variable, and we call the first sample x1, the second one x2, etc., and we divide by n, then if the number of these samples is tending to infinity, that means you do 100 people at a time, and you keep doing it for infinite number of times, for sure you'll find out what the true probability of voting, or true percentage of votes are going to be. Okay. Now, that's one interpretation, and but that's basically the practical interpretation that we have over here. So a similar kind of thing is in a simulation. You run a simulation, and you want to find out the probability of buffer overflow. So you run it. There's some random variables. So in the first simulation, you find that there were 20 million events, and a certain number of buffer overflows. It gives you probability of buffer overflow for the first one. Then you run the simulation again. Now you're doing the same sample. It's independent because you're running it again. The random number generators are independent. And you expect that the results are drawn from the same distribution. So you get the IID property, and then you get the second value for x2, and so on. And then you divide it, and then you see, what you present in your paper is that my mean of these 4 or 5 runs was this, and inherently what the reader is saying is, okay, if n is large enough, then we expect that your set of means is going to be actually the true value of the mean, in this case, buffer overflow. Okay, so the law of strong numbers is necessary for us to actually even present experimental results that come from simulations. Okay, so of course, if n is very small, like you do 2 runs, and you take these 2 things and divide it, well, that's not really particularly valid, because who knows, you may have gotten lucky. But if you do it for 10, 20, 100 times, then we can say that, okay, it's going to actually be a valid mean for that particular simulation system. Okay, so this is the law of strong law of large numbers. Okay, there's also a weak law which I won't go into, but this is what's going on over here. Any questions about this? Okay. Now I should caution this. There's a little bit of there's a little funny thing going on over here. When the law is stated, we just say that x are random variables, okay, and they're drawn from distribution, and you're taking these sums of these values that x1 is basically that x1 equals x1. It's really what we're saying over here. But generally speaking, what we have to do is to take these sub things, 100 people at a time, compute probabilities, and then take things across those. You could also apply it by saying, okay, if I want to find the average height in this room, or the average height of the Canadian population, I'll just pick somebody up and say, okay, you are a representative, okay, I'm drawing you randomly from the Canadian population, and this is your height, and then I can use that directly over here instead of taking these smaller samples. So the example they used for the election results was a little bit more complex. A simpler one would simply be to say, I just pick somebody at random from a phone book, ask you what's your height, and I keep doing that. And then if I do it often enough, I'll find the mean height of the Canadian population for sure. Okay, that's the other way of doing this. Okay, doing it the way I suggested, having samples of size 100, immediately exposes the question, well, how big should that be? Well, actually, that should be infinite too, right? And that actually brings me to the next one, which is the central limit theorem. Okay, so before I move on, so are there any questions about this? Okay, so let's look at the central limit. So the strong law of large numbers shows up primarily when you start doing simulations. That just gives you some theoretical validation that your simulations actually mean something. What about the central limit theorem? has to do essentially with the confidences, and we'll come back to this when we do statistics. But for now, I just want to state the theorem. Here we have, again, a large number of arbitrarily distributed random variables, okay? And, okay, so we'll just call them x1 to xn, and n is large, and we want to find that much more than that, and they're IID, so they're independent and identically distributed, okay? And they all have the same mean, which is mu, and same variance, so what we're saying over here is that, look, we're essentially sampling something that hasn't changed. That's why we get IID. So the easiest way to get IID is we're doing some kind of sampling from an underlying population whose distribution hasn't changed. Then we can say this. Basically, we can say that the distribution of this quantity x1 plus x2 plus xn minus n mu, okay, divided by sigma under root n, okay, tends to the normal 0, 1, the Gaussian 0, 1 as n tends to infinity. Okay, so basically what we're saying is this. We are doing we have some kind of sample. Again, let's say this is the height, okay, and we're taking this height, and we know that its mean is mu. So we did not know what mu was earlier. Now we can say, okay, we can use the strong law of large numbers, and we take n large enough, we can kind of estimate mu. So now we say we know mu, okay? So we know mu, and we're saying that the sum minus n mu. So this is essentially, remember where the Gaussian kicks in? The Gaussian kicks in when you have some kind of expectation. So here the expectation is that this sum should be n mu, right? It should be kind of n mu. So there's a little bit of jitter around it. What's the jitter around it? That jitter around it is this minus this. Okay, so this value expected essentially to be 0. And when we normalize it with sigma under root n, then this quantity over here is actually, in fact, a Gaussian. Okay? That's the central limit theorem. So it's saying that these values are kind of becoming, the sums of these values, I should say, are becoming closer and closer to a Gaussian as we increase n. So if you take more and more and more samples, and we find out what the mean is using law of large numbers, basically the sum divided by n is a large number, is the expected to be the mean. Then assuming that that is in fact the mean, then this quantity over here tends to n sigma. That essentially gives you the confidence interval when you're doing experiments. If you're doing an experiment, what you do is you compute the parameter of interest, like the packet loss rate or the expected, I don't know, expect service rate, the expected delay. These are all parameters of interest in any simulation. We take these quantities, and then what we do is we run this, we essentially subtract off the population, the expected mean, expected value here, and then this thing over here is going to look like a normal 0, 1. So what I can do is I can report this value over here, then I can put around it these error bars, and these error bars are really the confidence around it, assuming that this quantity over here, okay, which is the value, adjusted value over here, is Gaussian. So in other words, these are n0, 1, or actually I should probably be more precise. So n mu sigma square error bars, okay, depending on how you compute them and how you represent them. But we can assume that the probability mass of whatever, if these are drawn with, let's say, 3 sigma, we can assume that the probability mass of 99% lies between these confidence lines because of the central limit theorem. And what we have to do is to make sure n is large. So if you run 3 simulations or whatever, and then you plot these error bars, you know, this is not really good. We have to do at least 10, 20. We don't know what at least means because it depends on the inherent variability of the system. But, you know, 2 or 3 is too small. Okay, so these confidence limits are useful only as n tends to infinity. And the actual equivalence arises only at infinity. Okay, so there is no specific guideline I'm going to tell you right now how large is, but when you do statistics, we can start looking into confidence and so on, and then we'll get a little bit more precision into how large n should be. But all that is based on the underlying use of the central limit theorem. Okay? Any questions about this here? Okay. All right. So let me stop that. And okay. So these four theorems that I stated are used. These are the bread and butter of the simulation world. And do I want to talk about simulations directly right now? When you talk about hypothesis testing and so on, statistical validation, statistics, these will become much more relevant. But there is this fine line between probability and statistics, and these are in the probability side of things, and then we'll move to statistics side of things later. I'm going to change gears a little bit and talk about what is meant by joint probability distribution, and then for the rest of our class, basically I'll be talking about how to deal with joint probability distribution. All right, so so far we've been considering essentially univariate x. You have a single random variable called x, and x is distributed. It could be Gaussian or power or whatever, but we only think about one random variable. Of course, that doesn't have to be the case. Okay, we want to sometimes talk about combinations of random variables together or jointly. Let me give you an example of this. Okay, and let's say that we use the following random variable. Let x be the probability that it's going to rain today. Okay, or to be more precise, x equals 0 implies that no rain today, and x equals 1 implies rain today. So this is a Bernoulli random variable. Okay, and so it's a standard Bernoulli random variable with some probability. So I should probably say x is a random variable such that x equals 0. So it's an indicator random variable 0, 1. So we can think of rain today as being success and no rain being failure, and we can have this indicator variable over here. Now I'm going to introduce a new random variable called y. And y is a random variable such that y equals 0 implies no rain tomorrow, and y equals 1 implies rain tomorrow. Okay, so fine, I have two random variables, fairly straightforward. Now I'm going to ask you, what does it mean to say we consider these probabilities together, jointly? Okay, so remember that x is defined over an event space, a domain of 0, 1, right? So there are two events, 0, 1, and x has some probability distribution p over the domain 0, 1. And similarly, y is defined over the domain 0, 1 as well, being a Bernoulli variable. Now we can define something called xy. Okay, so we're going to say xy is a joint random variable, and we define it over the product of the domains the 0, 0, 0, 1, and 0, 1, 1. Okay, so xy, the joint random variable, has 4 values instead of 2. It can be rain today, rain tomorrow, no rain today, rain tomorrow, and so on, right? Rain tomorrow, no rain today, these 4 possibilities over here, right? So that is, in some sense, definition by example of what I mean by a joint probability distribution. So joint probability distribution over here is a random variable also, which has a larger domain. So in fact, if each of these domains, this is of size m, and this is of size n, then I need to have mn, okay, values. But let's ignore that for now, okay? So let's put some numbers over here, and then I'll take a break. So let's say that we have the following: p of pxy of 0, 0 equals 0.2, pxy of 0, 1 equals 0.4, pxy of 1, 0 equals 0.3, and pxy of 1, 1 equals 0.1. Okay? So what are we saying? The probability that it doesn't rain today and tomorrow is 0.2. Probability it doesn't rain today but rains tomorrow is 0.4, etc. And all these probabilities, of course, have to sum up to 1 because it's just a random variable on a discrete domain. Okay? So the important thing to understand is that we can essentially take two random variables and we can combine them together. Okay? And then the combination is also a random variable which also has a domain like a normal sense and also has to satisfy the same rules of probability, and then we can keep doing this again, right? We can say the probability of rain over 2 days is pxy, and they can introduce a third day, day after tomorrow, xyz, and then I can kind of combine those and so on, right? And in many cases, what we really want is to look at systems where there are many random variables in play, and we want to compute the probability that this particular random variable achieves some value. Like if you have 10 underlying things, you're going to say px, x1, x10 has the value 0, 1, 1, 0, 0, 1, 0, whatever, right? And what is the value of that? And we'll see in a minute why this becomes practically useful. Okay, so let me take a break and let you guys refresh. I'll leave this on the board. Are there any questions about this at all? Going on here? All right, because if you understand that xy is a random variable, then everything else becomes basically pretty straightforward after that. Okay. Well, thing over here, and as Omar pointed out, x and y need not be related. They need not be in the same domain. I'll come to that in a minute. Okay, so now what I'm going to do is to just intuitively show you some obvious stuff. So if we know that pxy, suppose somebody gives you a joint, okay? They say that pxy is this. I want to ask you, what is the probability that x equals 0? How do I know? What is the probability x equals 0? Okay? How would you do it? Anybody want? Yeah. It's 0.6 because basically what you're saying is that probability x equals 0 is nothing more than probability x equals 0 and y equals 0 plus probability x equals 0 and y equals 1, right? Well, why do we say that? First of all, because this domain is going to be a standard probability domain, in which case it's exhaustive and mutually exclusive, right? That's what we define a domain to be. It has to be exhaustive and mutually exclusive. If it's mutually exclusive, then these two underlying things are independent events, and so we can add them up. Right? So we are just following the rules of probability over here, the probability calculus, if you wish. And so, and then these two things, well, we know that from these two values. We just plug it over here, and this becomes 0.6. And similarly, you can compute the value of px equals 1. And that is, well, it's got to be 0.4 because it's 0.6, and x is a valid domain, so I can tell you that value as well. All right? So what I've done over here is the following. I'm giving you the joint distribution pxy, right, over here. And I'm asking you, given this, can you tell me px? And the answer is yes, of course I can. Can you tell me py? Sure, I can tell you that as well. And these are called the marginals. So this gives you px, and this is the marginal. It has a name. It's called the marginal distribution. Marginal distribution of x, I guess is what we're calling it, has to be of x. Okay? And similarly, we can compute py as the marginal distribution of y. Okay? Now, what we're doing for this is then to generalize from this, to compute the value of px equals any value x is nothing more than sum over all possible values of y, right? P x y x equals x, okay, y. All right. So what I'm saying is that if I want the probability at x equals 0, I keep x equals 0 over here, and then I sum in the joint across all values of y, and that gives me the value of x for x equals 0, and the same thing for x equals 1, right? So what you have to think of is that I have got the value of x fixed, and then a range over all possible values of y, and that gives me the value of x for that point. Okay, similarly, I do that for y. If I want to find the probability that y is something, I keep that value of y fixed, which is what I have over here, and then range over all of the possibilities of x, and that gives me the marginal value of y at that point. Okay, so is that clear for you? Okay, and once you go into continuous domain, the sums get replaced by integrals, right? We just say integral minus infinity to infinity. So in the continuous case, we'll just say the probability x equals x is nothing more than integral minus infinity to infinity pxy. Okay, x equals x, and then y dy. Okay, where this notation means that I'm essentially finding that point. I'm fixing the point x, and then looking at the essentially the value of the joint values for that over there. So we'll come to that in just a minute, but I'm just kind of motivating that you can do this in the continuous domain as well. It generalizes quite easily. Okay, so now an interesting question arises, which is that I'm giving you pxy. It's some distribution of pxy, and I'm saying, okay, looking at this, I want you to tell me are x and y independent or not. Okay, so I've got these things. So we have the coin toss and rain. Let's say a coin toss and rain. And when let's say this amazing thing happens, I toss a coin, comes up heads, it rains the next day. Okay, it's great. I toss it again, comes up heads, rains the next day. So I'm saying, wow, this is great. If I take the joint probability of coin toss and rain, okay, then I'm going to get P11 equals 1. It's fantastic. Okay, and everything else is 0, presumably. So in other words, if I wanted to rain, I just toss a coin, it comes up heads, it will come up heads. Somehow the low pressure which brings the rain also influences the coin in just the right way, or maybe I'm just a wizard or something, I don't know. But okay, but I'm going to turn the question around, which is I've given you this distribution. I want to ask the question, are x and y independent? And it turns out that we can, the rule for this is the following. X and y are independent if pxy, x equals some value small x, y equals some value small y, is nothing more than the product of the marginals of x equals x and p y equals y. Okay. All right, so that's what we're saying over here. That is that essentially what it means is like this. Let me actually show you. I'll leave this up and let me show you something first. So let's say that the marginal distribution of x for 0, 1 equals 0.2, 0.8. And let's say the marginal distribution of y over 0, 1 is 0.4, 0.6. Okay? What I can do is I can draw the table like this. And what I'm going to draw on this table is going to put x here and y here. And I'm going to put down 0, 1, 0, 1. Okay? So what's the probability x equals 0? It's 0.2. It's x equals 1 is 0.8. And y equals 0 is 0.4 and 0.6. Okay? Now, if I can represent the values here as a product of the marginals, okay? In other words, if pxy over here is 0.16, and this is 0.32, and this is 0.12, and this is 0.48, okay? Then this condition is holding. That is, the probability x equals x, y equals y is px, and the product of this and this, right? In other words, I can take this entry over here, and I don't need to tell you these values. I don't need to only tell these two values, okay? Let's think about it a little bit more. In this case, it turns out, because it's trivial, I need to tell you 4 values, these 2 values and these 2 values, and then I get all those internal 4 values, with mn entries, if x has a domain m and y has a domain n, I need to tell you just m plus n values instead of mn values if x and y are independent. Okay? So let's go back over here and look at this case. Okay? In this case, I want to test whether x and y are independent. Okay? So what I'll do is this. Let me just compute what's px, x equals 0. Okay? We said that's equal to 0.6. We already knew that. Somebody said that. And then py, y equals 0. Well, what's that? Okay? So that's just this value plus this value, it's 0.5. Okay? If this were independent, then pxy, x equals 0, y equals 0, which is just nothing more than pxy 0, 0, should be equal to 0.3, okay, if x and y are independent. But in fact, pxy 0, 0 is 0.2. Okay? So we can conclude that in this joint probability distribution, x and y are not independent. Okay? So the fact that it rains today somehow influences that it's going to rain tomorrow. Okay? All right? So this is actually quite fun. You know, what we did was I gave you just these 4 numbers which looked like they were picked out of a hat. In fact, they were picked out of a hat. I just picked them. Nevertheless, by figuring out the marginals, which we did using a simple rule, and using this definition of independence, okay, I can tell you right away that the probability of rain today influences the probability of rain tomorrow. Okay, which is pretty good. You know, it's not bad for 10 minutes work. So what's going on here? What's going on is that the joint probability distribution is very, very, very powerful. It's got all sorts of stuff in it. You know, it's like a box of treasures. You open it up, you take the marginals, and you get all these individual, it's giving you the individual distributions. And so if you say pxy, if I fully describe pxy to you, or pxyz to you, I'm actually giving you as information the independent marginal distribution, not the independent, but the individual marginal distributions of x, y, and z. I'm packing all that in for you because I can get the marginal solved with very little work, right? And then once you have the individuals, then computing whether they're independent or not is very simple. So all I'm trying to motivate you to think about is that the joint probability distribution is a very, very powerful beast. However, it is very large. Okay, consider that you have, you know, x has m variables, y has a domain of size n, and your z has, you know, whatever q. You're going to have to multiply these out, and if you have more and more and more, you get this explosion of values, and you need to know the precise value for each of them. Okay, and that's a lot of information. Okay, so it gets to be very difficult. So if you get the joint somehow, you're in wonderful shape, but you're very unlikely to get the joint. In all practical situations, you will never have the full joint distribution. You'll only have the marginals, and they may not be independent, in which case you cannot take the product rule. If these are not independent, if x and y are not independent, this cannot hold. You cannot do that. You can't just assume that these things are going to be the case, because we saw a case right here where, in fact, the marginals, the product of the marginals does not give you the value of the joint. Okay? So this is sort of a phrase you have to remember. The product of the marginals does not give you the joint unless the marginals are independent. Okay? And that sounds complicated. All I'm saying over here is that if you have 2 variables, x and y, if the product over here, the product can be used only if I can assume independence. Okay? And that's a very fundamental concept that you need to understand. Okay. Are there any questions about this? Yeah.
Does this dependency mean that one of the random variables is the function of another one?
Does it mean that there is a functional dependency of one on the other? Not really. It just means they're not independent. Okay. It influences so what I can say is that the fact that a certain thing happened influences the following, but it's not a direct dependency relationship. Okay. For example, let's take the case that you do a lab test, and you know the lab test indicates that, I don't know, you suffer from some horrible disease. Okay. And then the thing is that you have the lab test does not mean you actually have it, right? It doesn't mean actually have it, because there are cases where it's wrong. It's a false positive, right? So it influences the degree of confidence you have in the likelihood that you have the disease, but it's not a given. It's not like it is definitely there because it's a false positive rate. So when two variables are independent, are dependent, it doesn't mean there's a functional dependency that you necessarily have. It just means they're dependent. They're not independent. Okay, so non-independence is not the same as there being a functional relationship. There may be no functional. Okay, or if I make it more precise, if I tell you X and you know Y for sure, okay, then there's a functional dependency. But if I tell you X and your confidence in Y goes up, that is probability Y given X, okay, increases after you know what X is, then it's not a functional dependency, but still they're not independent. Okay, so there's a difference over there. There's a big difference over there. Okay, and this is what happens in your stochastic variables. You don't have, these are not discrete, precise variables. They're stochastic variables. Yes.
If we have a large set of joint distributions and say in a discrete space, is there any sort of thumb rule or heuristic rule that we can find out their dependency by looking at their magnitude? I mean, say like
you have a large number of joint distributions?
Say the cardinality of X is 1,000, the other one is 2,000.
Okay, so you have a large number of marginals in the joint, you mean?
No. We just have the.
You just have the joint.
Joints, yeah.
Okay.
So we have, say, something of magnitude of a
Million. Okay, million, yeah, okay.
But a bunch of these guys are very small.
Right.
And a lot of them are not a lot, like say 5% of them are larger.
Right.
Can we just focus on the
so the question is, can the structure, yeah, the structure, the question is, does the, can we determine independence or dependence based on the structure of the joint? The answer to that for me is pretty straightforward, which is that we only need to compute, in this case, the marginal for one value, okay, which is 0. And you have to compare it with the value of the joint for one value. If they differ, even one differs, you know right away that they're not independent. Because it has to be true for everywhere. It means even one value off is enough to indicate they're not independent. And that's probably a good enough rule of thumb.
Well, that we understand. Is
Yeah.
there a smart way of choosing?
Yeah, there is. I'm coming to that. That's what a Bayesian network does. Okay. The Bayesian network is exactly a smart way of doing things properly for joint variables. Okay. Let me just give you another simple rule, and then we'll move on to Bayesian networks. So I talked about independence. I want to talk about something called the conditional probability mass function. And this is, it's basically, let's see, okay, P x given y, x, I should probably say x equals x, y equals y, okay, and this is P x, y, x equals x. I should probably say so. Okay, which is equal to P. Let me just write this down and then P x, y, x over. Okay. So what you're trying to do is something like this. I have this joint distribution, and in this joint distribution, I have these two variables x and y, which are the independent, sorry, not the individual distributions. And I'm saying now the following. I'm saying, okay, I know the joint, and I want to know the conditional that x takes, in this case, the conditional that y takes some value, okay, conditional that y has taken the value small y, what is the probability, what is the joint probability that's going to happen, okay? And what we're doing here is essentially Bayes' rule, okay? Or sorry, not the Bayes' rule, the definition of conditional probability. This is just the definition of conditional probability for a joint distribution. What you're saying is that it is the pxy, the a and b, as you saw earlier, divided by py of y, the marginal of y. What are we doing? We're reducing the sample space and eliminating all those that are inconsistent with the value of small y. Okay? So for example, if you take the example over here, maybe it's easier to explain there. we say that what is the probability that we have rain tomorrow given rain today? Okay, and this is going to be Pxy 1 1 divided by Px of 1, because rain today is marginal distribution of 1, and this turns out to be 0.1 by 0.4, 0.25. Okay, so what I'm saying is this. I know that the probability that it's going to rain today and tomorrow, okay, is 0.1. Okay, that's fine. I got that from the joint. Now I'm going to ask you a different question. Okay, today has happened. I found out it rained today. Now that I've told you it's rained today, now you tell me what is the probability of rain tomorrow. Well, what's going on is my probability increases from 0.1 to 0.25. Okay, why has it gone up? It's gone up because I've removed everything in the joint probability mass function that has to do with no rain today, because that event didn't happen. Okay, so the conditional always has to do with time sequencing of events. Event 1 followed by event 2. Okay, what I'm showing over here is how, given the joint, we can use it to actually compute conditionals as well. Okay, so given the joint, because I've given you Pxy, I can compute Px from that. I showed you how to do that. And then I can also give you the conditional also from that, simply by dividing out the joint value by the marginal value. Again, this will explain to you why the joint is so interesting, because I can use it to derive conditionals from it. Okay, so I can tell you the probability of rain. So this actually goes back to the previous question. Are these independent or dependent events? Well, we know that rain today influences rain tomorrow because it caused the probability to increase. Okay, by knowing this fact that today it rained, in fact made it more probable that it would be raining tomorrow than in the abstract, I don't know anything going on kind of deal. Okay, so this is why these are not independent events. If they were in fact independent, what you would find is that it wouldn't change. Why wouldn't it change? Because you could just cancel out Pxy be Px Py. You cancel it out, you just get Py. So Py is Py, right? It's no information is gained by knowing this, and that's what happens when you have independence between the underlying events. Okay, so the coin toss happens, and you have rain tomorrow. If they're independent, you'll find that Py doesn't change at all, conditional on X happening. Okay? All right, so all this is essentially telling you that joint is a nice thing to know. I'm going to now just quickly tell you a few more generalizations. I've already hinted at those. So, well, X, we had the domain as 0, 1, but we could easily make it as 0 to m. So we've already talked about that. And then Y could be 0 to m, and you could certainly say that the joint has mn. Second, we can have continuous X and Y, in which case we define the probability that A is less than X is less than, what did I put that, A plus alpha, and B is less than Y is less than B plus beta, because remember, for conditionals, for continuous, we have to define in terms of mass in certain regions, is going to be nothing more than the double integral B to B plus beta, A to A plus alpha, Pxy xy dx dy. So again, what I'm doing here is I'm just defining to you what is the meaning of a joint distribution of two continuous variables. And what you can think of is that I have some kind of surface. If you look at the plane, above the plane I have some kind of surface. Okay, this is the xy plane. And in this surface, if I look at some point over here and look at a small region which is bounded, it is bounded in size by B, A, and B plus beta, A plus alpha, so a small little rectangle. The volume in that little cylinder over here is going to be the probability mass associated with that region over here. Okay, and of course, we're looking at the limit in some sense. The limit is going to be 0, but we're looking at that mass in that little volume. Okay, that's basically what's going on over here. Okay, so it's a very standard, straightforward generalization of continuous mass function for a density function for a in the two-dimensional case, or sorry, one-dimensional case, I looked at x and x plus delta x, or x plus delta, and I looked at the amount of mass over here. For the joint, I have two random variables, so my support has two random variables. I have to look at the amount of probability mass in that little volume over there. Okay, so that's a straightforward generalization. And then, of course, instead of having two, then I can have n random variables as well. I can have n random variables as well. Okay, so then it gets even more complex, and then that makes us worry. How can we even specify it? Okay, so let me motivate, and I guess I'm going to run over today. So I'm going to motivate the Bayesian network from here. So a Bayesian network is, at its heart, a practical tool for dealing with joint distributions. Okay, so you've seen the power of a joint distribution. It gives you marginals, it gives you independence, it gives you conditionals. Wouldn't it be nice if you knew the joint distribution? Now, the attack we're going to make on it is to show that there is independence. Okay, in other words, if we can find those parts of the joint that are independent from each other, that saves us a lot of time, because we can just multiply out the marginals and find the joint, and then we're in good shape, because once you have the joint, everything is available. So what we want to do is to start thinking about which parts of the problem are going to be independent of each other. Okay, and if they're independent of each other, then we can just take the marginals and multiply those out. Okay, that's the intuition in a Bayesian network. So what a Bayesian network does is essentially to explicitly capture the dependency relationships between variables, between random variables. And by putting down the dependency variables, all the things that are not there in the dependency diagram are going to be independent. Independent, we can just multiply them and get the joint probability distribution for free. Of course, in many cases, we don't actually need the whole joint. We just need some parts of it. Okay, so let me kind of show you. So let me first show you a Bayesian network and then explain what it is. So I'll show the example first. So in a Bayesian network, each node is a random variable. Okay, and the edge is denotes dependencies. And edges are directed. Okay, and so you'll have a link like this. This is called the parent. This is called the child in the obvious normal sense. And we say that the child depends on parent. Okay, and in fact, a child may have multiple parents, in which case I can say child depends on parents. Okay, so that's in a nutshell what a Bayesian network is. So let me do an example. Let's draw an example first, and then I'll come back to the mathematical formalism. So I'm going to consider the following system. I have a system where I'm considering TCP, and TCP, transmission control protocol, is what's used for reliably sending data on the internet. Okay, so in TCP, let's assume that we can have two possible problems: packet loss or acknowledgement loss. So I'll call this P, which stands for packet loss, or A, which is acknowledgement loss. So these are two different random variables, P and A. Okay. Then I have a random variable called T, which stands for timeout. Okay. So it might be just, I'm just going to tell you what packet loss and ACK loss mean. What I'm doing here is I'm modeling, let's say, a period of time for 1 minute. Okay, I'm just picking some arbitrary period of time. Let's say I'm picking 1 minute. Okay, in that 1 minute, either packet loss happened or did not happen. So what's the domain of P? It's just 0, 1. Similarly, in that 1 minute, either acknowledgement loss happened or did not happen. Again, the domain is 0, 1. Timeout happened or did not happen, 0, 1. So these are all very simple random variables that are 0, 1. Okay. Now, what I'm saying is that if there's acknowledgement loss, well, I send a packet, I wait for the packet to come back, or for the ACK to come back. If the ACK doesn't come back, I'm going to get a timeout, right? So acknowledgement loss, so timeout, the timeout event, okay, the random variable timeout or the timeout event depends on the ACK loss. So that's the parent, that's the child. Okay. Similarly, if there's a packet loss, I'm going to have a timeout as well, right? So there's an influence. A packet loss causes or influences the possibility of a timeout. Now, it may happen, in fact, that the packet is lost, but in that 1 minute interval, no timeout happened. Okay, it's possible, but it influences it, because this we know as our experts in the field, which is why this belongs in AI. Now, we have another possible thing going on, which is a duplicate acknowledgement. Okay, why would I get a duplicate acknowledgement? Well, when you send a packet with a particular sequence number, you get an acknowledgement back, okay? And sometimes if you get, so let me just show you here. Actually, I send packet 1 and 2 and 3. So I send 1, it makes it through. I get an acknowledgement for 1. I send 2, it doesn't make it through. And I send 3, I come back. And what I'll do is I'm going to acknowledge 1 again. Okay, why did I acknowledge 1 again? It says I got everything up to 1. I didn't get 2. So I get a duplicate acknowledgement. I got A1 and A1 again. That's called duplicate ACK. Why would you get a duplicate ACK? You get a duplicate ACK because of packet loss. You never get a duplicate ACK because of acknowledgement loss, because if the acknowledgement was lost, you know the packet got there, so you're never going to send a duplicate ACK. It's going to be a ACK that moves forward. You know, just to illustrate that, let's say 2 got through, but the ACK for 2 got lost. Okay, so this is ACK for 1, ACK for 2. This will actually say ACK 3. You won't get ACK 2 again. ACK loss will not cause duplicate ACK. All right, that's an independence event. We got a nice independent event which says that ACK loss does not cause duplicate ACK. We can just prove that just looking at this figure over here. So that's nice. And finally, I have this event called R for retransmission. And what it says is, if I get a duplicate ACK, I'm going to have retransmission. If I have a timeout, pretty sure I'm going to have retransmission as well. Okay? So I've shown these dependency arcs over here. All right, so is it clear what's going on? So all of these are essentially 0, 1 domain random variables. Either it happened or did not happen, right? And so we can start asking for we can start representing it in this fashion, okay? And we can start asking some questions about this. So the first thing we want to do is we want to characterize what does the joint even look like, okay? So for example, we can have the following. We want to compute the probability, for example, that the packet loss happened. Okay, I'm going to just simplify things. Let's say that the variable P means packet loss, small a means ACK loss, T means timeout, D means duplicate ACK, and R means retransmission. So what we really have is a joint probability distribution of 5 variables, which are P, PADTR, PADTR, which has the normal meaning that P equals 1 means that it happened, and 0 means it didn't happen. Same for DATR. So we can start asking, what is the probability of P A not A, D not D, T R? What is this probability? So this means what is the probability that we have a packet loss but not an ACK loss, and no duplicate ACK happened, but the timeout happened, the retransmission happened. Okay, this may be something that you really care about, because it tells us that there's a retransmission due to the timeout and packet loss events. Right? This is probably something interesting for us to figure out. We want this, in fact, to be 1. Right? If the packet loss happens, if our code is working well, we should find that the timeout should happen and the retransmission should happen. So we want this one to be basically very close to 1. Okay? Is it going to be true or not? How do we know? So that's a very interesting pathway for us. Similarly, we may want to compute the probability, okay, of P bar A D, or maybe just one probability AD, right? So if an ACK loss happened and I got a duplicate ACK, well, that should be close to 0. If I see this, then I know that I'm in big trouble. Okay? So what I'm trying to say over here is that we don't want everything about the joint function. We want some things about the joint function. Okay? So for example, PAD is going to be, or PA equals 1, D equals 1, and then we sum over all the other possibilities of the joint. Okay? But that's how we do it if we had the joint. Now, what we can do here using the Bayesian network is now we can start writing down things which don't influence each other. Okay? So for example, over here, we're saying in this case that P, A, and D from our system are in fact independent events. So we should be able to look at this, immediately write down this is equal to 0. I don't need to tell you what the joint is. The Bayesian network gives me that value right away. Okay? Gives me the value right away. So that's one example. But let's say we want to compute something else. And in the example over here, I have a somewhat more complex. I want to do this. Hopefully, it will make the ideas a bit more clear. I want to compute the following problem. I want to do what is the probability that we have P given R. Remember, I can extract all the conditionals I want from the joint. Okay? But I don't have the joint. What I have instead is I have the Bayesian network. How can I use the Bayesian network to compute P given R? Why is this an interesting event? What it says is a retransmission happened. Okay, I measured a retransmission happened. I want to know what is the probability that in fact a packet loss happened. In fact, that the retransmission was due to packet loss and not due to ACK loss. Okay, so what is the probability of that? So let's use the Bayesian network to compute this. So all right. So what is the we first of all let's compute P of R. Okay, because maybe I should put it like this. So P of P given R is nothing more than probability of P and R. Okay, capital P of P and R divided by probability of R. Okay, because well that's the way that conditional probability is defined. So let's see if we can get the denominator first. What is P of R? Okay. So P of R, or maybe I should just write this here, R, which is probability of R, is equal to P R given T, P T given P, P. Maybe that does not explain what's going on. T given A plus P. Okay. So, oh, I missed a step. No wonder it's okay. Let's just write this. Okay, P of R equals P. Okay, so what does the first line tell you? The first line says P of R is, so I'm saying that the R depends only on two things. It only depends on D and T. It doesn't directly depend on P and A. They'll come later, okay? So let's for a moment focus on this part of the system. And I'm saying that the probability that R happens is just either T happened and then I can tell you that what is the probability of R given that T happened, or D happened and what's the probability of R given D happened. Okay? Because R depends only on D and T, I can write that equation down right away. Okay? Everybody clear with that? It just comes straight from this. I don't need to worry about P, R given P directly because I'm going to extract it out using the Bayesian network. So I can write this equation down. Then what I can do is I can unpack P, this small t over here. What is T? T over here is P, T given P, and the probability of P itself, and P T given A, right? Again, from the definition of conditional probability, this is how I get. So I just replace that over here, and I get P R given T, P T given P, P. Okay, and this is where the confusion, okay, capital P, and that's a small p. And then I'm unpacking this one over here. So P R given D over here this one is coming from this. It only depends on one previous event over here. Why did I get that extra term over there? P R given TP plus PT given A. Oh, sorry. I have to put a parenthesis over here, okay? Because T depends on two events over here. T given P plus T given A. So I put those things over here. T given PP plus PT given A plus PR given D, PD given PP, okay? So I'm just using the definition of the conditional to move back in the chain of events. So I'm going back, and at this point we can compute R, because basically what you're assuming is that in the Bayesian network you're going to annotate these links given these conditional probabilities, okay? And I'll tell you what that is in just a minute, so maybe I should just describe that. What I'm assuming is that on this link I'm going to store the value of P T given A and P T given P, okay? And over here there are no priors. Over here the prior is P, so I'm going to store P D given P, and here I'm going to store P R given D and P R given T, okay? Let's just look at these values in yellow for just a minute, okay? What I'm saying over here is that these parents over here don't have a link to them, okay? So these are independent events, okay? That's what the Bayesian network says. There's no dependency between D and T. So the joint distribution of D and T at, that R depends on are captured by these two conditionals. We don't need to know anything more about where they come from. We just need to know these distributions. We don't need to know the correlation, because there's no correlation between these two independent variables. So what we do is we are storing in yellow essentially how the child depends on the parents. And what we're saying is that the distribution of R then depends purely upon these conditionals over here. Okay, if you know these, I can tell you what it is. And in fact, that's what I'm doing over here. By knowing the distribution P D given P and P T and the distribution of T, which in turn depends on these two, I can unpack everything and tell you the distribution for R, the probability of R, as this equation over here, where R given T is this, T given P is this, and so on. Okay, so let's go back to the abstract for just a minute. I have a node, I have the edges directed. What I'm going to add is that each child stores its probability, its probability conditional on parents, conditional on each parent. Okay, which is what I've shown in yellow over there. Okay, so this allows us to essentially compute P of R. Okay, now in the notes what I've done is I've also computed a little bit more. In fact, to get the numerator is a little bit more work, which I'm not going to, which I suggest you should take a look at and read, because it is important. But I'm going to, in the interest of time, just going to tell you about the formalism for a Bayesian network. Instead of going into details. So in the notes it tells you how to similarly solve P, P, and R. Okay, it's very similar to this, and then you plug these two things in, you get probability of P given R. So in other words, by doing this you can do this. So let's just look at what a Bayesian network means, and I want to. So in the final analysis, how the Bayesian network represents the joint probabilities like this. We define some event E, some vector E, okay, as some set of random variables, E1, E2, etc., En, okay. So in our case, this was P, and this was D, and this was R, etc., okay. And I want to compute the probability it takes on any particular thing. So, but what we can say is the probability of the vector E, which means the complete joint distribution, is given by the product of I equals 1 to N. The probability and underlying okay, so let me erase this over here. So this equation explains everything you want to know about Bayesian networks. okay, in one equation. What am I saying over here? I'm saying that if I want to know the joint, I just need to know the product of each random variable ei, such as p, a, d, t, and r, given the parents of ei, okay, which is in fact these values over here. So at each node, I just need to know how it's conditional on the parents, okay? And of course, for these guys, they have no parents, so I need to know the actual value of p and a, okay, that kind of comes down over here because there are no parents, and I just need to know probability of that event directly, so it's also part of the equation. However, once I know this, I can get the full joint distribution simply by product. And how am I getting this? Because the parents relationship captures all the dependencies, okay? So what's going on is this. The joint is great and wonderful, very hard to compute. And Bayesian network says, look, I'm going to exploit all the independence relationships. In fact, it turns out the only relationships that matter are the parent-child relationships. And these can be written down by an expert. You can say, well, you know, this is not dependent on that, that depends on this, etc. So drawing this graph is not easy. Okay, in fact, there are many books you can read about how best to draw Bayesian networks. In fact, it turns out if you just rearrange things, it gets much harder. And there are sort of easy ways of doing things, and it's not obvious that the easy ways are actually computationally efficient. But setting that aside for now, from the mathematical perspective, what we've done is that we've captured in this graph the entire dependency structure such that we can now write down the joint merely as a product of the underlying conditionals. And this is the beauty of the Bayesian network. It allows us a practical tool to discover parts of the joint, and as we discovered, allows us to pick out those things that we want. We just want P and R. We don't want P and R and not this and not that, etc. We can get essentially all of those for free by just looking at the graph over here. Okay. So as I said, I am a little bit over time, so I would suggest that you go with the example and see how we compute P and R, okay, by using this network over here. All right, we'll stop here, and I'm in the process of updating the queuing theory chapter. There's some typos and so on. I should have that done by the end of the day today. So if you want to download it and print it or something, wait until tomorrow afternoon, and it'll be the latest version there. Right now, the version still has some problems.